Okay, welcome everyone. Today we're going to look at some bias mitigation and building trustworthy models, taking off from all the bias problems we've looked at before this. So here's an outline for this lecture. We're going to first look at the concept of fairness just briefly, and we move on to look at some of the ways that we can achieve fairness, and one of the most important things is through balanced data sets. We'll look at fairness metrics, and we'll look at this notion of detecting bias, and a little bit about mitigating them, and also towards trustworthiness via explanations. So fairness, the concept fairness, might be quite hard to describe because it depends on the kind of task you're looking at, but very broadly we can say what fairness means in the form of ethics is to treat individuals and groups fairly and not just use their data in ways that would have unjustified adverse effects on them. And very simply we can just think of fairness as the absence of bias. So with that we want to make sure that we can do fair, we can detect fairness, and we can test for fairness in our data set. So the most common way that people like to think about how do we build models that are fair to begin with? How do we know that our models are fair? Okay, so we know that from some of the examples we've seen, for example, the compass model, we know that these protected attributes, sensitive attributes such as gender, age or race could play a part. If we include these features, then our model might end up being biased because it can find some correlation, some harmful correlations between like the gender and maybe whether they should be hired or not, okay, and their race, and maybe they should be withheld and they might reoffend again. So the best way is to say, okay, let's just remove these attributes and let's train our model. Now this is, a very sensible thing to do, right? If the model, okay, we here means the model is unaware of protected attributes, then, if the model doesn't get to see, what's the gender or the race of the examples it's looking at, then the decisions that it makes are going to be fair. Because the system now cannot see whether this person is female or young or black or whatever it is, right? And cannot kind of discriminate against them. But this is, this sometimes works, right? This is a very sensible thing to do. There are many examples where, by removing these protected attributes, you can actually see that the model is fair and it doesn't show any discrepancy when it makes decisions. But we know that there are potentially what we call these proxies, right? These other attributes that could actually stand in for these protected attributes, right? They could be, for example, like if the address of a person, the neighborhood where they live might, be highly correlated with their race, and these kind of things. So we've spoken about these proxies. So even if we remove protected attributes, sometimes the presence of proxy attributes could still cause the system to be biased. So one of the best ways, and in fact the most, the thing that everybody or every data scientist should know and should definitely practice, is to think about working with balanced data sets, right? We should always go back to our data, simply because we know our model is, almost always just going to be as good as the data that we feed it with. So make sure that when we create data sets, we are intentional about them. We make sure that we don't just collect data. If you were to go out there and collect data, you don't just collect what you can get your hands on, right? Just make sure that you collect the data that you need in the right proportions, and also with the right intentions. So if you're to know you're going to be, collecting data, and you're going to know that there's one class, okay, like one group of people, like women or, men or whatever in your particular data set, they're going to be what you call the minority class, then try to proactively go out there and say, let me go and see if I can collect more of this data so that, I can get more, more representation of it. And, we know that in reality, we can speak to data scientists and we'll know that this is obviously ideal and this is what everybody wants to do, but this may not be possible, or it could even be very expensive. In reality, sometimes collecting real data is often very expensive. It comes at a high cost, or sometimes even scarce. Sometimes it's even hard to get some kinds of data. So this is the reality of it. So what people do, right, there are many hacks around this. Hacks or maybe even techniques that people definitely practically use. And one way is by undersampling from majority class. So, assume that maybe the data set has mostly, data set of Caucasians and not a lot of data sets of non-Caucasians. So maybe you say, okay, if I have a very big data set, like 100,000 data sets, and 90,000 of them are Caucasians and 10% are from my minority class, then let me just reduce that. Let me just make sure I have exactly 50-50. So I might take just 10,000 majority class Caucasians and 10,000 minority class non-Caucasians, and I'm done, right? And because now I have 20,000 data sets and they're equally balanced. But we can see a slight problem with this, because that means we've actually lost some data, right? We've actually thrown out data from our majority data class. So this could be, a bit controversial. We've actually lost valuable data. But, it's possible. It depends. If your data is very small, if you're going to make it even smaller, this is a huge problem. If your data set is large, then you want to consider, is it feasible? What can I, is this something possible? Which 10,000 data set, examples am I going to get? All those kind of things. And of course, on the contrary, instead of undersampling from the majority class, why don't we try to oversample from the minority class? So if we go back to that example where we have 90,000 majority class, 10,000 minority class, so let's try to maybe create, some more minority class. Very simply, okay, let's say I undersample. Let's just say I take 50,000 majority class. But now I still have 10,000 minority class. So what I do is maybe I just randomly reuse or duplicate examples from the minority class. So that means I'm just going to have copies, like 4 copies of each of my minority class. Just say I just duplicate them 4 times, 5 times, so now I have 50,000 minority and 50,000 majority. This, may or may not work, simply because we have, we might end up having duplicates, and we don't know whether these duplicates, are really going to help, because they're just identical data sets appearing like 5 times and so on. So this is another consideration. It depends on what we're working on and whether it's appropriate to do it. Another very common and practical things that people do is something called data augmentation. Okay, this is in fact very common, very practical, and very useful. What we can do is we can just make some small transformations to our existing data, especially since we're talking about the minority data set, so that we can increase its size and diversity. Right? So instead of just creating duplicates, which we think it's not going to really enrich the data set, one thing that people do in image processing a lot is just to run some kind of transformations, like flipping the image or rotating the image, resizing it, okay, cropping it, changing the brightness and contrast. So if we just have one image of a cat like this, so if I rotate it, then I have, another image. So now this is an additional image to my minority class, right? So if I only have 10,000 images of cats and I have, 90,000 images of dogs, so now by doing some kind of um, transformations or augmentations, I can now multiply my images of cats, by changing it a bit. And this is actually very, very practical, useful, and works very well. Um, if we are thinking about textual data, what about text? What if we have like textual data that's, very scarce for one particular class? Um, we can shuffle the words. Okay, we can do things like this. We can, maybe shuffling the words might end up making sentences having different meanings. So again, we have to do them with caution. Um, we can replace some words with synonyms, right? So if we replace some words with synonyms, so now we have, new data, which is kind of like the same data, but we have synonyms instead of those words. Or we can just insert or delete words at random. Okay, there are just many, many ways that people do this data augmentation, um, and not just restricted to these, but these are just like some very common and immediate ways that we can see this being done. And this is very practical, as I said, and useful, and may even work very well. But of course, you have to analyze, the situation, whether what you're going to do is appropriate or not. Imagine you have images of digits, okay, like the number 6, number 9, number 1, but they're images. If you do something like rotation to it, this will actually change the image, right? This will actually, change the number 6 if you rotate it like in a vertical way and then flip it again to the other side. You might end up getting the number 9, and that's actually wrong. If you want the number 6 to be preserved as number 6, you might be able to rotate it, but maybe not flip it. So think about what kind of transformations are suitable. And actually, one of the most common ways that people do it, apart from these basic ways, is what you call create synthetic data. So now, instead of just, we take one step further from augmentation, and we actually just make new data. But this new data is going to be different to what we have. So there are many techniques in this area, and now with generative AI, we have tons of ways, but a very common traditional way is something called SMOTE, okay, where very simply you can just sample some examples close enough to your example minority class. Okay, so you take like other minority classes near it, and then you kind of try to sample a data set between, these two classes. So you actually generate a new data set for your minority class. Okay, so this is, kind of has to be done mathematically. So if your original data set, is very unbalanced like so, because one class has, very big distribution compared to the other one, and after applying SMOTE, you actually generate new data sets to have like, equal distribution. So this is, now you're seeing like it's a bit more sophisticated, powerful, than just, duplicating. But augmentation is also quite powerful. So these are very, very common things that people would do even, before going any further. Data scientists would be very aware of all these kind of techniques. And so we move on now. Now that we've seen some considerations for data, let's look at what we call fairness metrics. So people have come up with many metrics, right? How do we actually measure whether, a particular model we have built, whether a particular data set we have is actually fair? Right? So a metric is a measurement to evaluate something. It's, used a lot in science. And a fairness metrics compute values that can be used to show whether a data set or model contains bias toward a particular group of people for some protected attribute. So now we can kind of quantify and say, how can we actually measure whether, this model is showing some kind of bias? So a very, very basic and common way is to start with something called the confusion matrix. So the confusion matrix, okay, as all machine learning people would know, is just a matrix, okay? It's like 4 numbers here that's going to show whether a particular model, right, made a decision on a particular data set, and let's say that data set is a historical data set where those decisions the model is trying to make has an actual correct answer. Okay, so the actual values is basically what we call a ground truth. So if we look at compass, right, we know that the positive class is whether a criminal or former criminal has a high risk of whether they will reoffend a crime or not, and a low risk is whether they will probably not reoffend. And we can say that we just give these two what we call like a label. Okay, so if they have low risk, they are at 0, and if they are classified as being high risk, they have label 1. Okay, but the machine learning model might give a prediction based on its own inner workings. But on the other hand, if we have historical data of past criminals, of whether they have reoffended or not, we have what we call the actual labels or the ground truth. So what we can do now is we can plot, okay, this confusion matrix to see whether what the model has predicted, how much is it accurate and how much is it off compared to the actual values. So if we see this, a confusion matrix contains the number of cases within a data set where we can compare what a model predicted with the actual values. Okay, so if we see these 2 white boxes here, the true positives, basically saying the model has predicted that this number of people out of our data set, they are high risk people, and according to the historical data, yes, they were indeed high risk people. So meaning it has done it correctly. It has correctly classified people who are high risk in actual fact as really high risk. And the same with what we call the true negatives, where the people who were really low risk, and the model also predicted that these were low risk. So basically it has done the correct prediction. But the problematic ones that we're more interested in is what we call the false positives and false negatives. Okay, and these are what we call problematic ones. Okay, the false positive here means that the model has classified, a person as high risk. Says, okay, this person here is going to reoffend, but in actual fact, they didn't. Right? That means it has falsely given the positive label to this person, but in actual fact, they're negative. And so, out of, let's say, a large data set of 10,000, ex-criminals, for example, we're just going to count how many people, how many such examples has our model classified as, positive, but in actual fact, they're negative. Okay, they did not reoffend. And the opposite is the case for false negatives, where, they have, the model has incorrectly said that this person will actually not reoffend, but actually they did, right? So these two are problematic. So what's the problem, right? They could end up being unfair to individuals. For example, if you have a very high false negative in your model, what it might do is it might end up not arresting certain kinds of people. Let's say, if you are a privileged group, like for example whites, who actually reoffended. So this is, the high false negative, meaning they were classified as low risk, but in actual fact they're high risk, right? So these people kind of were not arrested, right? They kind of walked free. but that might happen at the disadvantage of other individuals, for example, the minority group, or the blacks who did not reoffend but were kept in custody. So, this is where we understood the compass thing. Now, note that this positive and negative, this class being 1 and 0, not always, will sometimes mean something different. So in this case, the positive class 1 is actually something that is undesirable, that might cause undesirable for, like certain groups, like will reoffend. But in another example, the positive class 1 could mean something else. For example, whether this model is going to predict whether someone will be given a loan, right? So in this case, you're saying that, some people were, in the false positive here will mean some people were given a loan, but in actual fact, they should not have gotten the loan, right? So that's a false positive, and the negative class is kind of like a more negative connotation. They actually were not, it's like a kind of more or less, they will not be given a loan, and in actual fact, they should have gotten a loan. So these two classes, it's not always that sometimes the positive things mean something actually positive. So you really need to understand the label, what this positive and negative class means, and what the false positive and false negative as a result mean for these different scenarios. So if we were to go back to the compass problem, where we saw that this false positives and false negative cases were problematic, so what people can do is divide that data set for the two different groups. For example, you have a privileged group and you have an underprivileged group. And if you were to see in this particular example, the false positive rate, okay, or percentage for your underprivileged group is fairly high, right? Remember, the false positive here are people where the model has predicted that they will reoffend, but in actual fact they didn't, right? So this is high, comparatively speaking, to the false positive rates of the Caucasian ones. So this is where they are being discriminated, right? So the matrix for the group on the right suffers much more false positives, which is undesirable. So this is where we can detect that this model is biased, because we can see that the false positive rate for the underprivileged group is higher. And likewise, we can see that the false negative rate for the privileged group in this instance is higher than the false negative rate for the underprivileged group. So in this case, they were favorably let go. Okay, the model has said, they actually didn't reoffend. The people who didn't reoffend, but actually they did, okay, was much higher for them than it is for the underprivileged group. So when we this is like a very basic one, but there are also a bunch of other computing, other fairness metrics, like statistical parity difference, disparate index, equal opportunity difference, and so on, where that are more sophisticated and more common as well, which is going to highlight these biases in more detail. So the first one that we're going to look at briefly is called demographic parity. So what this is saying is, in order for a model to be fair, it requires equal proportion of positive predictions in each group. Okay? So what that means is it's just looking at the true positive class. Okay, so the number of true positives divided by the total number of people. So let's say this is true positives for blacks divided by the total number of blacks should be the same for the number of true positives in the white group compared to, divided by the total number of whites. So in compass, we can say the same proportion of will reoffend, will be present in each group. Okay, so we're not looking at the negative class or whatever, we're only looking at the positive class. And what this is saying is demographic parity is achieved if the percentage of blacks will reoffend is going to be the same as the percentage of whites will reoffend. Okay, and this is irrespective of whether blacks on average are more likely to reoffend than whites. So this is just saying, as long as we get, this proportion, we don't care about any other factors, we don't care about stereotype, we just want to find the numbers. Okay, if we look at another example in a university admission model here, which I've taken from Google, suppose you have, a bunch of candidates that apply to enter, a very, difficult to get university. And if we see, we have two different groups here, right? We have the accepted ones and the rejected ones. Okay, so this is the accepted ones is, the positive class is if they are being accepted, and the negative class is if they are being rejected. Okay, but the two groups here, okay, the groups that we're interested in are, like, let's say a majority group and a minority group. We don't know what the majority group and minority group are, okay, but we just know that we see that there were 16, people, let's say, out of 100 people got accepted for the majority group, and only 4 people got accepted for the minority group. However, if we look at the total, okay, the total number of majority group is actually 2, 3, 4, 5, 6, 64. 64 plus 16 is 80, right? So there are 80 in total of this majority group, and 16 got accepted. So 16 out of 80 is 20%. And then when we look at the minority group, there's 4 here and there's 16 here, so there's 20 of them. So 4 out of 20, total of 20, is also 20%. So what we're saying is, in this particular data, we can see that the model has satisfied demographic parity, because both the majority and minority group have the same percentage of acceptance rate, or true positive. The next one we're going to look at is equal opportunity. Now, equal opportunity, we have something called true positive rate. So true positive rate, TPR, is the proportion of positive instances that are correctly classified by the model. Okay, so in Compass, what this means is the proportion of those who would have reoffended, okay, that were correctly classified as high risk. Okay, mathematically speaking, we can just say, the true positive rate is the total number of true positives, meaning whatever the model and the actual, the people who were really, truly reoffended, divided by the total number of true positives and also the true negatives. Okay, the total, numbers that were correctly classified, and this is the proportion of it. And for a fair model, equal opportunity tells us that the true positive rate for an underprivileged group, okay, just going to put it TPRU, should be the same as the true positive rate for a privileged group, TPRP. Okay, so if we were to calculate these numbers that we can get from our confusion matrix, if we plug them in, we're basically saying that for these two different groups, they both have equal opportunity, right? Those that would have been reoffended, whether they were black or white, if they both have the same, proportion, then we know that this model is somewhat fair, right? So this is one metric that is useful. But a slightly more strict, a stricter version of that is something called equalized odd, right? So now we have a notion called false positive rate. False positive rate is a measure of the proportion of positive cases that were incorrectly identified or classified as positive in a test. Okay, so the false positives, as we know, is we have incorrectly classified them as positives, but they should really be negative. So false positive, number of false positive, divide by false positive plus true negative. So in Compass, the false positive rate is the proportion of those who would not have reoffended but were unnecessarily classified as high risk. And that's kind of what it means. And we now have this notion called false positive rate. But in equalized odd, what it wants for a fair model to have is both the true positive rate for the two groups we're interested in should be equal, and the false positive rate for both groups should also be equal. So the TPR of U should be the same of TPR of P, and the FPR of U is equal to the FPR of P. So in actual fact, this is actually quite a strict criteria, and this is also very hard to achieve in reality. Okay, but these are all kind of measures that people have taken so that we can actually measure, or we can detect bias in either our model or in particular our data set. And without going into too much details just yet, maybe I'll do it next time, is now that we know a little bit about how bias can be detected, using some very classic metrics, there are also strategies. People have also come up with bias mitigation strategies, meaning how can we get rid of this bias now, right? We saw that dealing with the data, preparing our data, okay, some of them are here, what we call pre-processing. So what we can do is, when we have a machine learning model, what we can do is, before we put our data into the model, we can apply some kind of bias mitigation to, let's say, our training data. So some of them is like what we've seen, what I've spoken about in the data, getting the balanced data part, okay, like the sampling part, or we perturb them, right? Like we add some additional things to them, we transform them, we augment them, and there's a whole bunch of other techniques. In other words, we just prepare the data well in a way that this data will be as fair and correct as possible before we even feed it into the model. And then we also have techniques inside the model itself. So very commonly, like neural networks have many regularization techniques. So things like to make sure it doesn't become too biased. So while we are what we call training our model, so we can do all kinds of things, right? We can use certain architectures of the models. We can regularize. Okay, these are again a little bit out of the scope of this lecture, but there are methods that people do within like the model itself, so that when the model is training, it can overcome these biases. And finally, of course, we also have post-processing methods that where once you have actually trained your model, you can then see from the results of the model, and then we can do one of these different things, right? We can actually get rid of the bias once the model has been trained. And like I said, I just want to talk about this briefly right here. I'm not going to go into details just yet, but you can of course look into this paper to get more details. And so now we want to talk about prevention is better than cure. So we saw methods to to detect bias, and also very briefly at how we might overcome some of these biases. But what if we can build models in such a way that we don't have to go through that, right? Or not just we don't have to go through that, but even before we build models, we know that these models are good or trustable, okay? And what we know, right, we know very well that some machine learning models, such as neural networks, are not really what we call interpretable by nature. And we know this nature of these black box models. So these black box models don't tell us how did they come up with these models? Why did they come up with those results? Um, and and that's not building trust, right? When people are presented with a model and say, oh, here's a model where you're not going to be able to see how it makes its decisions, but it's going to tell you whether you should hire someone or not. And you might not want to trust a model like so. So the whole point of something we call explainable AI is to really deal with this issue. And what explainable AI does is it involves building an explainable module, okay, or interface that has data visualization that can take part and that can actually explain what the model is doing. So it has data visualization and scenario analysis features to machine learning models. So what we have is we have our training data, we have machine learning process, and then we have an explainable module. And this explainable module is normally visual, right? Because it's something that can explain either in words or pictures what is going through inside this, initially black box model. So while it has done that, people now can trust the model more, right? And this is the whole point of it. If we can build these black box model to have what we call an explainable component to it, we can build trust between the people or the user who make use of these models. And this is clearly one of the best ways to go right now, right? Instead of just using a black box model. And there are some very well known, there are many explainable models right now. I'm just giving some examples. There are well-known tools like SHAP, LIME, even very common techniques like saliency maps, and also there are many tools made available by many companies and institutions. So there are all these well-known modules, and there are even more. So here are just a bunch of examples of how explainable AI is actually being used in practice in reality. So how some of these models look like. So LIME is one of those where it can explain. For example, if you're trying to, it says that, let's say one model has come up and said that this is an image of a guitar, right? But it says it's an electric guitar. So it's saying, okay, but why did it say it's an electric guitar? Then it says, oh, because seems like it shows the reason it's saying it's electric guitar is because of this particular part, which it has taken to come up with this class. Or it's saying, well, it's an acoustic guitar, okay? When a model is explaining, has decided that it has come up with acoustic guitar, it has shown the reason I have come up with acoustic guitar is because of these parts of the images. And you can see these are the acoustic parts. And maybe another model says, well, this is actually a picture of a Labrador. And we say, why did you predict, model 3, why did you predict it as a Labrador? It says, oh, because look, this is kind of what I saw. And this is why I predicted it. So when it says, okay, this is actually correct, right? It is a Labrador, but it's a bit more than just a Labrador. And then with SHAP, which we will see in a bit, it comes up with, feature importance. It comes up with like a score for different features that has, come up with decisions. And with things like saliency maps, it comes up with heated regions, kind of says, okay, if I'm, describing this as a dog, this is where I have described it as a dog by, looking at this particular area, right, and not something else in the image. And, explainable AI is used quite a bit in sports, and, tennis is no exception. Back in 2022, IBM Watson, came up with, when you start watching a tennis match, it starts to give, oh, there are these two players, players 1 and player 2, they're playing a match now, and then it kind of says, oh, this is what Watson, okay, what our AI believes, player 1 has a higher chance of winning this match, 54% against 46, And then it says, okay, well, that's Watson, but why? So if you click why, it kind of says, okay, if we see why player 1 is going to win, we can see that player 1 actually leads player 2 in the IBM Power Index. So the IBM Power Index is like a ranking, based on players' ranking. So player 1 is ranked higher than player 2. And then it says, well, also the grass court surface, okay, this is Wimbledon, which is a grass court. It says the grass court surface favors player 1 over player 2. Maybe they have won more matches on the grass court. And also, it says, well, another reason why we think player 1 is going to win is because, there's a head-to-head. Player 1 and player 2 have played 5 times before this, and player 1 has won 4 out of those 5 matches. So it says, that's why we think player 1 will win this. And then, you can also see, other things. You can click on other things. So, this was like a nice intuitive interface where, if you watch a lot of sports nowadays, as we mentioned, you can see these kind of statistics popping up because there's the explainability. Just taking the data and coming up with these kind of explainable module that tells people, oh, okay, well, you may not know who these players are, so you might think that these kind of explanations help you to say, okay, maybe, if you want to go and bet, you might then take this information and bet to see whether you're going to win or not. If we go back to explainable AI and another example, let's say this is a slightly different example. This is a textual one. So, for example, if there's a system that wants to find out whether the stock value of a particular stock is going to go up or go down. And the way this is done is sometimes, of course, based on various different things, but maybe one way is to look at financial news. So to see, what kind of news is out there, and then see what people are saying. Are people saying good things about this company right now, or about, this particular stock? And this is something called sentiment analysis. So meaning we're going to see whether are people generally saying positive things about this, or are they generally saying negative things about this, or is it just neutral? Okay, so based on this, we might be able to guess whether the stock is doing well or not. But to do this, we actually have to see a lot of text, right? Maybe on social media like Twitter or X or wherever, or news portals. And what this AI algorithm can do, if the AI says, well, yes, you should, the stock price is going to go up, you should buy, or you should sell, or whatever. And then and you're like, but why? Why are you telling me that, the price is going up? So it says, well, look at this one thing. This first sentiment is saying Brazil's rail stocks are world's best as foreigners pile in. So it's saying, okay, the word best here is saying, that this is a positive class, okay? It's saying that the stocks are going higher, okay? It's a positive sentiment. And the color, okay, the redder the shade of the word, the more it is important in making that decision, okay? So the word best has given me, that this was an important word, okay? So this color is higher than this, okay? This word has more importance than the word well, or than all these other words in determining that this is a positive one. And you say, okay, yeah, I can see that best is, a good one. And then this one says now negative U.S. Treasury market pain amplifies worry about liquidity. So yeah, the word pain and the word worry, right, liquidity, these are all like negative words. So these words have, really contributed towards saying that this is a negative sentiment. And likewise, there are a couple more examples here, okay? And the opposite can be said, like the bluer the word, the blue words are kind of giving like, the opposite. So the word policy is actually like a more positive word. Okay, like, it's not really giving, contributing towards making this negative, but the words prolonged, political, and crises are like important words and making it look negative. So if you can see that your model has made decisions like this, you say, yeah, okay, I think it has done like correct, you know, sentiment analysis. So I will follow its, I will follow its advice on whether I should buy the stock or not. Um, and um, and the more shade was blue, the more the word pushed the algorithm toward making the opposite decision. So what you can do is you can use one of these libraries, right, like Lime or Shap or a whole bunch of other libraries um, on top of like an existing normal machine learning model. And this is what, some people do, some scientists and students do, researchers do, in order to get some trust on their model. And so the IBM's AI 360 model is quite a well-known model that's actually very intuitive. So this one, you can, it kind of can show whether there is a bias. It's a bias detection tool that can show graphs for different metrics. It is also, you can assess whether the tool did a good job in detecting the bias by seeing how much you understand these diagrams. And then it also has some bias mitigation methods. It has a selection of methods to choose from, and it also has a comparison between original and mitigated results. So maybe you can do an analysis by going to like the link and by checking whether it has done a good job at it. And with Shap, which is another tool, what you can do is, the Shap is actually short for Shapley Additive Explanations. And what it does is, it takes like certain features, so the features, as you know, those inputs like whether the age, the sex, the blood pressure, the body mass index, okay, and then it's kind of giving, explanation. It's going to say how much has age affected, whether, I don't know, whether this person has a health condition or whether, whatever decision it's making. And it can show that, whether one feature is positively affecting, increasing, the likelihood of this output being this, or whether it's negatively affecting, the output that the model has made. So this is again something that you can play around with some examples that you will be given. And this is, like Shap is just a Python library. So for those of you who are developers, you can just install it and run it over your normal machine learning model. And Lime, as we saw earlier, let's say you want to explain a specific prediction, like, we saw the prediction with this image just now, but you can also apply it on like text, right? Whether it's, how your prediction is tied to some features, right? So the idea is to create many new samples around X, okay, or like X is your feature value, by replacing some of them with others pulled at random from the data set, and to see whether the prediction of those new samples, what those predictions of the new samples is going to be. Okay, so use those new samples and predictions to then you have to retrain, you have to do some extra work on a linear model and use the fitted weights to understand the local contributions. So, I mean, each of these tools are quite complex in their own right. So if you want to know more, you can actually, look at the papers and the work that people have done on it. And if we go back to saliency map, which is really, really visual, we can see that, whether a model has bias or not. Okay, so we can, saliency map actually show which region the model is paying attention to when making a decision. So let's say this particular model, the job is to come up with one word at a time. Okay, so it is generating one word at a time when it's looking at an image. So it says, it's generated the word and then it says a man, right? So the second word it's predicting, it's a man. But it says, oh, what am I doing when I am predicting the word man? Oh, I'm looking at the picture of the computer, right? So here what you say is, oh, hang on a second. why is it saying the word man when it's looking at a computer? Because it has correlated the computer with gender. All right, it's assuming that a computer is, mostly used by men, right? So this is saying this is, um, a bias prediction. Firstly, it's not a man; it's a woman, right? So it's a wrong caption, right? But also it's wrong for the wrong reasons. And this one is saying, okay, a woman sitting in front of a laptop computer, and so when it is trying to predict the word woman, it's actually looking. So if you have two different models, you can say that, okay, this is a bias model because it has correlated laptop with a man, and this is a correct one because it has really predicted a woman as a woman by looking at a woman. And here we have an example. It says, it is a picture of a man holding a tennis racket. Okay. However, when it is trying to predict the word for man, instead of looking at the man, it's actually looking at the tennis racket. So this, even though it has come up with the right caption, but it is biased. Okay. It has come up with the right caption, but for the wrong reason. So we know that this model is a biased model. Whereas let's say we have another model, it says a man, okay, when it's predicting the word man, it's actually looking at the man and not something else where it should correlate the man with. So, we can use all these kinds of tools for, bias and image captioning above. Model has made correct and wrong captions, but for the right and wrong reasons. So it's very important that we build trust between humans and machines, like, because as people who use machine learning models, let's say whether they want to use it for hiring people, for making medical diagnosis, whether they want to know whether a person has high risk for a disease or whether they will recommit a crime, all of these, it's so important that the model doesn't have any bias. The model is explainable, is secure, it's transparent. There's so many aspects to trustworthiness because as users and as machines, there's so many aspects to this. So the more we can trust a model, the more we can actually use the model without feeling like there's going to be any harm done to anybody. And finally, I just want to talk about this notion of interpretability versus explainability. So a model that is interpretable is a model whose workings are transparent to the outside, or what we call the glass box models, meaning we know how it works. So such models do exist, right? The interpretability is the degree to which we can understand the cause to a decision. Okay, they're tightly, they're linked. So, for example, if you may or may not know, people who are in models like linear regression, logistic regression, decision trees, naive Bayes, these are some examples of machine learning models that are actually interpretable because we can actually understand what these models do, and we know from the results what they mean. However, there are a bunch of models that we know, those black box models. These models are not interpretable, meaning we don't really know how they work. Okay, some examples are like polynomial regression, random forest, or good old deep learning models that we know pretty well by now. And for these models, we can say that explainability, on the other hand, focuses on explaining the decisions made by the model. Okay, so they're tightly linked, right? Interpretability is just whether we know or not whether these models work or not, and explainability is actually, focuses more on whether the model is able to explain itself, right? Interpretability is to do with us as the users, whether we can understand, and explainability means whether the model can explain what it how it has made its decisions.